Well, hello again. This is the part 3, the final one of my talks in week 3 on noise pollution. This is about control of noise. So you've all heard about soundproof enclosures, but one of the things I need to point out that there's a common confusion between acoustic absorption with acoustic transmission, and some or so-called acoustic tiles, which you see in some rooms and ceilings to improve or change the acoustic character of the room, are usually sound absorbers. And the illustration I give is that an open window is a very effective sound absorber. The sound goes straight through it. It is also an effective sound transmitter. So we need to think about, if we want to enclose a sound source, what is required. And there's a thing called the mass law. And what that says is that if you double the mass of a partition, it will result in a 6 dB reduction in the level of sound transmitted. And I'll just leave this slide here for a few seconds. And you can see that depending on the type of enclosure, ranging from solid brickwork up the right-hand side, which can give you an effective sound transmission class or reduction in sound transmission of 50 decibels. In other words, if you had a sound level of 80 decibels in the room, you could expect in the next room, which with a brick wall between the two, that you would have 30 decibels. And down on the left-hand side there, you can see that a glass window is only effective about 25 decibel reduction. And it's directly related to the weight per unit area. And that gives you an indication of the noise reduction with typical building types, light frame and masonry. Masonry means brick or concrete. And in effect, the best you can do really is about 35 decibels. But then there's a problem if you have to get air in and out of the enclosure. And even small gaps can dramatically reduce the effectiveness of a partition. And I'll be talking a little bit more about this particular diagram in class. And I can relate to you some interesting field work that I did, and complaints about sound being transmitted from room to room. But we'll talk more about that in class. And if you want to read through the calculation there, you can get a bit of an idea of the effect of very small gaps. So there's something about double glazing. STC stands for sound transmission class. And that's just another way of indicating the isolation between two adjoining areas or two adjoining rooms. And I've given here a, it's, you can see by the date, it's quite a long time ago. But this is some work I did in the Tasmanian College of Advanced Education, which is now the Hobart Matriculation College on Mount Nelson, in their main auditorium, when it was sealed off to produce 3 different auditoria. And I did some actual measurements, and you do that by filling one of these spaces up with sound, with a loudspeaker, and with a particular spectrum, and then you measure the sound level in the following room, or the other room, and you measure that in octave bands. So these are the octave bands, third octave bands. So it's quite narrow, quite a narrow spectrum. And you can see that if the normal mass law applied, you'd get a field transition class of 40, whereas these partitions performed rather less than that. Well, what you say is that those partitions met a sound transmission class of 35, and this one a sound transmission class of around about between 25 and 30. So what can be done to reduce the environmental noise? Now, this is the six or seven now, actually I've made it up to 7, principles of reduction of noise. Now, the first thing you would look at is to reduce the sound of the source. And there are a couple of videos there you can look at, particularly that one about a jackhammer. That's jackhammers are notoriously noisy, and this one was designed to have a minimum vibration, minimum noise. So that's an interesting bit of engineering design. And as I mentioned, I think somewhere else that fans, if you make an efficient fan, it's likely to be a quiet fan. And there's something there about the Hong Kong airport noise mitigation you might like to look at. So that's reduce the sound of the source is the first thing you should be thinking about. Then next is enclosing the source. And you can buy specially designed enclosures. And one of the things that you would find is that the material they use has got to be very heavy because of the mass law. And so you can find that lead, sheet lead, is used for many of the enclosures. Steel is not so good because you can get the resonance effect, the skin of a drum or something like that, and the noise will be transmitted straight through it by resonance. So the next one is to increase the distance between the listeners and the source. And we've already talked about the inverse square law. Then you can increase the attenuation with barriers and vegetation. And there's a bit more about that in later slides. Then you can enclose the listener. And this has been something that has happened in flight paths below aircraft. Rather than relocate people living in those flight paths, the authority spent money to provide additional enclosure and additional soundproofing in their dwellings, like double glazing and sound-rated walls. You could relocate the source or the listener, so that happens. You would not want to have a aircraft landing over your house. So one of the things they try and do is move noisy industries like aerodromes as far away from residential areas as is practical. And the example I give is that there are some very, very noisy industries which are deliberately located in the flight paths adjacent to aircraft comings and goings. So that's a good example of sensible location of noisy sources together. And as a really last resort, to provide hearing protection, but that's not really an option, as I say there. So the increasing the distance, let's have a look at that now. There's the inverse square law, and that if you had a sound transmitted equally in all directions, would give you typically 6 dB decibel reduction. 20 log R1, R2 is 20 log 2, which is about 6. So that's the maximum you could get. But what can happen is that there are surface effects, and you can have things like water, which reflects the sound, it doesn't absorb it. And so in reality, the noise reduction with doubling of distance can be something between 3 decibels and 6 decibels. The other thing I wanted to point out is that absorption, heavily forested areas appear to be a good, or they are a good visual barrier, and they are an effective absorber at high frequencies. And we already looked at the relationship between frequency and wavelength. But if you're looking at the frequencies round about the audio level or lower, 50 hertz, the wavelength is 6.6 meters. So a wave with that wavelength won't even see most trees. It'll just go straight through. And that's one of the difficulties with acoustic noise control, is controlling the low frequency components of the spectrum. And there are other factors like directivity, if the source is pointing directly at the listener, air absorption, wind and temperature gradients, ground absorption, and as I've mentioned, attenuation due to barriers and trees. So I've given you some formulae here, and that relates the sound pressure level, SPL, with the power level. And if you put in various factors there, you get a very simple formula, which says that the sound pressure level is the power level minus 20 log the radius from the source, minus 11, you can see where that comes from, minus a few other factors. And that's to do with directivity, absorption, and attenuation. So it's quite a complex calculation, and that's even before you get to the patterns and the topographical effects which we saw in air pollution. So there's another reference there you can have a look at. So the next thing is to look at the effectiveness of barriers. And again, that's a bit of a problem because you can have sound, as it's a waveform, it can be transmitted and it can be reflected and it can be diffracted. So what the listener gets on one side of a barrier is a combination of the three. And there is some calculation you can do based on what's known as the Fresnel number. And I've given you some details there, which you can have a look at. And it's very heavily dependent on the wavelength. And here are some figures. It hasn't given the height of that barrier, but you can see roughly from the relative size of the truck and the house and so on, how much goes through the barrier, how much might go over the barrier. And the same thing happens in the horizontal plane. Finally, hearing protection, I've just said something about it there. But particularly in an industrial situation, there are requirements to use hearing protection if your partial noise index gets above the required or the regulated level. And just one other thing that will happen if there is any likelihood of hearing damage, then you must get regular tests of your hearing, or your workforce must get regular tests of their hearing to see if there's any gradual change in their hearing acuity. And now we come to look at what I call the bottom line for noise control. And this is set out very nicely in Australian Standard AS 1055. And it works this way. You start off with a base level of 40 dBA, and then you adjust it. That's chosen as being a a quiet, rural background noise level. You adjust that by the character of the sound permitted. So the bass level, if there are tones or impulsive noise really readily detectable, would be reduced by 5, and tones and so on, just detectable. And there are other adjustments due to the time of day, evening, -5, nighttime, -10, and so on. So you start off with 40 decibels, and that as a base level, but if you had impulsive noises, that goes to 35, and if it was during the nighttime, it goes down to 25. Then you have a look. Oh, and there's a neighbourhood. If you're in rural or outer suburban areas, no adjustment, but if you're in a general suburban area, +5, or heavy traffic, +10, and so on and so on. So now you look at the amount in decibels, dBA, by which the adjusted noise level exceeds the acceptable noise level. And this is what I call the bottom line. If the margin is between 0 and 5, you would not expect any reaction, public reaction. And that goes up to, if the difference between the expected level or the calculated or the measured level was 20 to 25 decibels, you would expect threats of community action to vigorous community action, and the extreme 25 and over. So that's what I call the bottom line. Right, I've put some threshold concepts in here to get you to think what noise level would be acceptable and what would be the effect of exceeding this level, why dBA, and what affects sound pressure at the receiver. So that's it. I'll be going over some of these details in class. And as I said, I'm going to give you some demonstrations of sound and the physical sound, and then we'll talk more about this what I call the bottom line of sound measurement and assessment of the effective effect of sound pollution. Right, thank you for your attention, and as I say, I'll be in class and we'll talk more about it.